Hi everyone, in this video we're going to cover lesson 113. So what I would like you to do is let's begin by completing this investigation number 1. You're going to remember how to plot complex numbers on an eigenplane. So just a reminder, an eigenplane kind of looks like a Cartesian plane where the horizontal axis represents the real part of a complex number and the vertical axis represents the imaginary part of a complex number. So for instance, if I'm plotting the number 2, okay, the first number in the set, then I'll be going 2 steps on the real plane, and that's it, because it has a plus 0i part, okay? So let's do another one, 1 plus I. So the real part is 1, the imaginary part is 1i, so that's why it's at this particular point here. Okay, so 3i, in other words, would be right on the imaginary axis. Okay, so you continue to plot all these other complex numbers on the eigenplane, and then after you're done, number 2, draw a line segment that represents the modulus of each number. So for instance, if I'm looking at my first point, this line segment would represent the modulus of this number. And then here's another one that represents 1 plus i's modulus. And then here, that represents the modulus of 3i and so on, okay? Number 3, find the angle theta that the line segment encloses with the positive part of the x-axis of each complex number. The counterpart of this is like, think of your normal cast rule type questions. You're rotating from the positive x-axis. So I'm going to do the first one here. For number 3, the angle theta enclosed by, let's call this maybe Z1 for the first complex number, Z2, Z3, and so on. I can say that Z1 has a magnitude or modulus of 2, and then we say that the theta, we call this the argument, is 0. Okay, for magnitude of Z2, the 1 plus I, while using Pythagorean theorem, I know that this is 1 squared plus 1 squared square root. So square root of 2 would be the modulus, would be the length of that line segment, okay? And then for, this is number 2. And then number 3 is for angle. So let me label them properly. And then here, so for the angle of Z2, then this is, well, 1, 1. This is isosceles right triangle. So this must be pi over 4. For the third complex number, which is 3i, magnitude is, modulus is 3, theta 3, or argument of that number, is right at the y on the y-axis, so we know that this is pi over 2 also. Okay, so continue to work these out, and then for number 4, you answer the conceptual question. Given a complex number, what is the relationship between the angle theta and the rectangular coordinates? Okay, so rectangular coordinates would be like 1 0 1 1 0 3 and so on. Okay, what's the value of the angle if the complex number is real and imaginary? So try to answer those questions after you plot the points, okay? Okay, so hopefully from the investigation, you found 2 very important relationships between a complex number and how it can be represented using, or how it relates to the modulus and the argument when you plot the complex number on the eigenplane, okay? So we say that if we have a complex number z equals to x plus iy on the eigenplane, then we can label certain parts on the diagram where we have the modulus of the complex number and the argument theta. And we can say that cosine theta can be represented using x over r, and sine theta can be represented by y over r. Okay, this is a very important relationship because if I now rearrange these two trig ratios, x can be written as r cos theta and y can be written as r sine theta. And we know that x and y represents the real and imaginary part of the complex number z. As a result of this, z equals to x plus iy can be expressed using r cos theta plus I r sine theta. If I factor out r, the argument or the modulus of the complex number, I have cos theta plus I r sine theta. Okay? And in order to save us some time, instead of writing cos and sine, we can use the short form r cis theta, right? So cos I sine theta, cis. And we call this the polar form. Okay, so r here represents the modulus of the complex number, and it is a real number, and r is greater than or equal to 0 always because it's just the modulus. And then theta represents what we call the argument, okay, of the complex number z. And in most books, you're going to notice that theta will be represented from 0 to 2 pi. In some other books, it is also common practice to have theta belongs to negative pi to positive pi. Okay, so it happens also. Okay, so you have the Cartesian form and sometimes rectangular form of a complex number looking like this, and polar form because you're representing using a radius, right? Really, it looks like a radius, and then theta is the angle, okay, if you plot on polar coordinates. So example 1, let's take a look. Write square root of negative square root 3 minus I in polar form. So we need to know both the modulus and the argument. So start with r. R is negative root 3 squared plus negative 1 squared. Okay. So this is 3 plus 1 square root of 4, which is 2. What about theta? Theta, or the argument of negative root 3 minus I. Well, if you consider, let's plot this on the argand plane first. Okay, so negative real number minus, so we're in this quadrant here. So we're talking about, this is the argument of negative 3, square root of 3 minus I here. Okay, so we'll be looking at pi plus the arctan of 1 over root 3. Okay, so 1 over root 3, we have pi over 6. And so this is 7 pi over 6 is the argument of the complex number negative root 3 minus I. So putting this together, negative root 3 minus I is 2 cis 7 pi over 6, just like that. Okay. Example 2. Write 3 cis 3 pi over 4 rectangular or Cartesian form. So here we know that we gotta use cosine and sine to do this question. Let's write this down. 3 cis 3 pi over 4 is equivalent to the modulus 3 times cosine 3 pi over 4 plus I sine 3 pi over 4, like that. And then using our, cheat cast rule, whatever you call it. Here is the location of 3 pi over 4. It is in the second quadrant. So I know that cosine is negative. This is negative root 2 over 2 plus sine is positive. So this is still root 2 over 2. So expanding, this is negative 3 root 2 over 2 plus I 3 square root of 2 over 2, just like that. Another way to represent complex numbers is using what's called Euler's form or the exponential form. This notation was first used by Euler in 1748, And basically, Euler says that, well, let's combine. This is like the most elegant form in math, I would argue, because you got trig, you got your cosine sine, you got your special constant e, the exponential function, and then you have a real part, you have the imaginary part. This is beautiful. Okay, so Euler says that we can represent cosine theta plus I sine theta in the form of e to the power of I theta. So here, when I have two complex numbers, z1 equals to r1 cis theta 1, and which can be written now as r1 e to the power of I theta 1, and z2 r2 cis theta 2, which is equal to r2 e to the power of I theta 2 in polar form or Euler's form. Then these two complex numbers are equal if the moduli are equal, r1 equals r2, and also if the theta, they're coterminal angles, they're equal. So theta 1 is equal to theta 2 plus 2k pi, where k is an integer. Okay, so we can identify identical complex numbers using this fact. So why Euler's form? Well, because we can use its property, we can solve a lot of problems later on. If I have to take powers of complex numbers using exponent laws, we can even use Maclaurin series. And this allows us to work using some sort of polynomial, right? So let's use the Maclaurin series to show that Euler's form e to the power of I theta is indeed equal to cosine theta plus I sine theta. So let's recall first. What does the Maclaurin series of e to the power of x look like? You can use a formula booklet also to give you a hand. It is x to the power of k over k factorial in this form. Okay, so let's apply this to e to the power of I theta. So I have k equals 0 to infinity. And then x now becomes I theta to the power of k over k factorial. Okay, so now we have 1 plus, what do we have? K is equal to 1. I have I theta over 1 plus k is equal to 2. I have I squared. You know what? Let's just plug it in. 2 factorial I theta cubed 3 factorial I theta 4 for 4 factorial, one more, and then dot dot dot. Let's represent that using dot dot dot. And then now I see a bunch of powers of I theta. What I'm going to do is I'm going to put down the argand plane showing somewhat like a unit circle. Think about that. Okay, beautiful circle. What are these numbers then? 1, I, -1, -I. You see why. Okay, so here I have 1 plus I theta. Now, I squared, I times I, that's -1. Theta squared over 2 factorial. Plus I cubed, I times I times I. This is -I cubed. So basically the idea is that I have, this is equal to I, this is I squared, this is I squared times I cubed, this is I to the power of 4, and so on. Okay? Okay, so I cubed is -I. Negative theta, I theta over 3 then. You know, let's do that. With 3 factorial, I theta cubed, I mean. Okay, so I to the power of 4 is just 1. So plus theta 4 over 4 factorial. Now, I to the power of 5 is the same as I to the power of 1. We go back to the top. So this is positive I. Theta 5 over 5. Factorial plus dot dot dot. Okay. Now I'm going to group every other term. 1 minus theta 2 factorial plus 4 factorial plus dot dot dot. That's one group. And then I'm going to group all the terms containing I. Factoring out I have theta, and then minus theta 3 factorial, plus theta 5 factorial. What do you notice? If you recall, cosine x has a Maclaurin series of 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial plus dot dot dot. And sine x has a Maclaurin series of x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot dot dot. Minus plus doesn't matter at the end. Okay, so what we are seeing in front of us is actually e to the power I theta, equaling the real part is cosine theta, and the imaginary part is I times sine theta. Okay, so this is shown. Okay, that's it. Okay, so you have just used the Maclaurin series to show the Euler's form of a complex number. Okay. All right. Let's take a look at example 4. Express the square root of 2e to the power of I 5 pi over 4 in the form a plus bi. Verify your result using GDC. Okay, so the first part, I think we're comfortable with that because root 2 e I 5 pi over 4 is simply root 2 times cosine 5 pi over 4 plus I sine 5 pi over 4. Okay, so if you want to consider, where are we? 5 pi over 4. 1, 2, 3, 4, 5. We're in quadrant 3. We're right here. Okay, so both cos and sine are negative. This is square root of 2, negative root 2 over 2 plus I, minus actually, root 2 over 2. Okay, times everything by root 2. Root 2 is 2. 2 over 2 is 1. So this is negative 1. So how do you do that on a calculator? Okay, now let's take out your calculator. Go to math. And then you use your right arrow. Scroll over to complex, the MPLX. And then look at the menu there. The menu allows you to actually turn a complex number from polar form to rectangular form using item 6, or turn a number from rectangular form into polar form using number 7. Okay, so that's what the menu look like. But the first thing is you have to first enter your number. So square root of 2, second function e to the power of I. So I is the shift of the decimal point button. Okay, and then 5 pi over 4, and then make sure you go to the right after you enter the Euler form of your complex number. Go to math, scroll over, turn this into rectangular form, and then you get negative 1 minus I as a result. Okay, so I'm going to put the note here. Okay, moving on to example 5. Given the complex number z equals to 4 plus 3i, find the conjugate z star, right, and negative z star in Euler form. So the negative of conjugate of z. So remember, conjugate means that the two complex numbers have the same real part, but a negative, right, opposite imaginary part. Okay, so we know that for sure in rectangular form, just to remind ourselves, this is the number that we're thinking of. Okay, So 4 plus 3, this is z. Z star is 4 minus 3i. So it is right here. Okay. And then if I want this in Euler's form, we can say that, well, for z equal to r cis theta, from the diagram, I think it's quite obvious that z star now looks like r cis 2 pi minus theta, or simply negative theta. Okay, so let's represent it on the diagram here like that, and here like that. Now, what about negative z star? Let's work in rectangular form first, I guess. So negative z star would be negative 4 plus 3i, right? Just like that. Okay, so negative 4 plus 3i. And let's complete the chart by also, I know the question didn't ask for it, but negative z would be negative 4 minus 3i right there. Okay, so let's connect. And then one more here, just like that. So notice how the conjugate and the negative conjugate, or z and negative z, they're basically 180 degrees or pi radians apart from each other. Okay, so if I want to complete this relation, then I can say that negative z is equal to r cis, what is it? Theta plus pi. And for negative z star, this is r cis pi minus theta. Okay, if we operate in Euler's form, then the magnitude of z is obviously 5, because 3, 4, 5 triangle, Pythagorean theorem, and its argument, it's arctan 3/4, okay, which is like, we're talking about this theta here. This works out to approximately 0.644 radians if I round it to 3 significant figures. In other words, z star then would be 5 cis negative 0.644, or in Euler's form 5e to the negative I 0.644, or negative 0.644i, it's fine. And then what else do I want? I want negative z star. This is 5 cis pi minus the angle, which works out to 3.14 minus 0.6. Using calculator, probably is better, is 2.5i. Okay. So maybe I'll just include that the negative of a complex number, they're basically separated by pi. Okay,